Jupiter's icy moons hold more liquid water than all the oceans on Earth combined. If we are going to find alien life in our solar system or establish deep space colonies, this is where we have to go. Reaching that water requires surviving a brutal environment. We have to cross hundreds of millions of miles of vacuum, punch through ice shells tens of kilometers thick, and withstand a constant bombardment of lethal radiation from Jupiter's magnetic field. Our traditional method of space exploration relies on point design spacecraft, massive, single-use machines built for one specific purpose. These are incredibly expensive, and because they are rigid designs, they cannot be upgraded or repurposed once they leave the launch pad. The problem is mass. Protecting a probe from Jupiter's radiation requires heavy shielding, but drilling through kilometers of ice requires heavy power systems. On a traditional spacecraft, the weight of the protection eventually crowds out the weight of the scientific tools, making the mission physically impossible to launch. To solve the mass problem, researchers at MIT have proposed staged deployment. Instead of one giant ship, missions are built from a fleet of interchangeable, standardized geometric modules that can be launched separately. By standardizing components like docking rings and power interfaces, we create a flexible technological ecosystem. This allows us to scale a mission over time, adding new sensors or propulsion units as our budget and technology evolve. But before we can land modular habitats or heavy melting probes, we need to understand the terrain. We have to map the hidden geography of these alien oceans from orbit. In the deep space environment, hardware will eventually fail. Building for modularity ensures that a single broken component doesn't end the entire mission. The first phase of this strategy is orbital reconnaissance, led by NASA's Europa Clipper and the European Space Agency's JUICE mission. These spacecraft carry magnetometers to measure how Jupiter's magnetic field interacts with the moon's. Because salt water is conductive, it creates a secondary pulsing magnetic signature. By measuring this induction response, scientists can calculate the ocean's exact depth and salinity without touching the surface. Europa Clipper will gather this data through 45 rapid flybys, diving as low as 16 miles above the surface before retreating to avoid a fatal 500 rem dose of radiation. The JUICE mission will take a different approach at Ganymede, entering a sustained 9-month orbit to gather high-resolution, long-term data on the moon's interior structure. Both missions use ice-penetrating radar to bounce radio waves through the crust. This allows us to locate subsurface lights and map the precise boundary where the ice shell ends and the liquid ocean begins. Mapping the invisible structure of the water is a mandatory prerequisite for physically breaching the shell. Phase 2 is subsurface access. This cross-section shows the scale of the challenge, a 10-kilometer thick ice crust above a 100-kilometer deep ocean. Traditional drills would seize. Instead, thermomechanical probes powered by small modular reactors will melt through the ice, sinking under their own weight. Once the probe breaches the shell, it serves as a communications hub, releasing autonomous robotic submarines, or XO-AUVs, into the abyss. These submarines use micro-electromechanical systems to keep their scientific instruments light and energy efficient. While the subs explore, the melting probe remains at the ice-ocean interface, serving as a docking station for data exchange and battery charging. This robotic beachhead effectively transforms an impenetrable alien ocean into a networked scientific laboratory. The final phase is the human element. The robotic data we collect will dictate the exact locations where humans can land and survive. Ganymede is the prime target for settlement because it is the only moon with its own intrinsic magnetic field. As seen here, this field creates a mini magnetosphere that deflects Jupiter's radiation, dropping surface exposure to a survivable 0.08 sieverts a day. But even on Ganymede, survival depends on adopting a modular approach to every piece of infrastructure we build. Standardizing the electrical and mechanical interfaces across every suit, tug, and habitat allows a settlement to survive using a small inventory of universal spare parts. By using these standardized connections, a colony can sustain itself by swapping components between different systems, reusing a motor from a decommissioned space tug to repair a life support unit or an airlock. A permanent settlement on Ganymede would serve as a vital industrial outpost, utilizing local resources to support further exploration. Settlers will harvest the moon's ice to manufacture rocket fuel. By chemically splitting water into hydrogen and oxygen, they can fill modular fuel tanks directly on the surface. Pairing this locally harvested fuel with modular propulsion systems creates a sustainable transit network, allowing us to push even deeper into the outer solar system. Exploring Jupiter's moons isn't just about finding life. It is about building the fundamental refueling architecture required to make humanity a permanent, multiplanetary species.